How you doing, guys? My name is Fetah. I'm with Group 2. We're the thermally improved battery pack design. And to answer some questions here, what's our problem? Right now, our problem is uneven thermal distribution, causing degradation to our central battery cells. With that, we plan on designing a battery pack with a heatsink to allow for even thermal distribution, which will in turn give us longer battery life. To talk about that more with us now is going to be our designer, Anthony Ramirez. Thank you, guys.
And here we have Mr. Anthony Ramirez, our man on design. Anthony, tell us a little bit about this.
This is our battery pack, our thermally improved battery pack, where we have 9 batteries on this level. This is a cross-section of half the battery pack. It stacks up 3 layers tall, making 27 batteries total. Each of the batteries has aluminum tubing that goes around it, and that tubing helps dissipate the heat that is generated by these batteries. We have aluminum tubes that run through the battery pack to reduce the air inside the battery and allow for more conduction between the batteries and the air, and convection of the air. Here we have a sample of our ANSYS where we run our model through the heat generation of the batteries.
And here we have Mr. Tetteh-Nartey doing our ANSYS modeling. TT, what can you tell us about this?
So on the left, we modeled our control pack, and from the image you can tell we have very ununiform temperature distributions, as it's very hot in the middle and then eventually reaches ambient temperature towards the out. And on the right here, we have our design of the battery pack, and you can tell that we have a much more uniform temperature distribution from the batteries.
Improving battery health, you would say.
Yes.
Sounds great. Thank you, TT. And here we have Mr. James Pousson. James, what are we working on today?
Well, we are going to an SURC conference, so I've been writing abstracts just for both the project and into the conference, and I've also been working on the poster board, just sort of blocking out everything we've been working on.
Sounds good, James. Are you excited for the conference? What are you expecting over there? And how do you expect these conferences to compare to the final senior design?
I am excited for the conference. I'm expecting just to stand around and meet a lot of people. I think in terms of differences between the expo and the conference, we'll have a lot more time to run testing before the conference, so we should see a lot more data. But in terms of senior design, we'll definitely see good work in showing off the battery pack and its design. So,
Sounds good, James. Great to see you. Great to see some good work from you. Here we have Mr. Dean Schepisi. What are we working on here, Dean?
This is our discharging circuit. As you can see, we have our 0.1 ohm power resistors. We have 2 in series, and there's going to be 4 in parallel, giving us a 200 milliohm resistance that's going to draw enough current to discharge our very high capacity battery pack in a time that's less than the typical. So probably around an hour and a half, 2 hours to discharge the whole thing.
And Dean, with that, looking at our advanced battery pack, why are we needing it to discharge so fast?
So with a normal discharge of a battery pack this size, the load wouldn't generate a high enough temperature difference in the pack to be able to model the way we want to, and it would also just take too long. So discharging at such a high rate, at around 300 watts, will allow us to have a steeper curve that will be easier to observe than the long time to discharge at 1 amp. Because with this, we'd be drawing about 8, 9, close to 10 amps, depending on the voltage in the battery pack. And also we'll be able to generate more charging cycles, so we'll be able to have more data to compare.